Alrighty, good morning, lads and ladies. Welcome back to Calc 1 Honors. First things first, I just want to let you know, I did go ahead and post the video from our last class just now, just a few minutes ago. It's uploading in the background, should be there soon. Sorry I didn't do that last Friday, but it is up now, or at least it is uploading now and will be available as soon as we finish class today. I want to remind you that the Brain Bowl is still looking for folks. If you enjoyed Asha's presentation last week, then I strongly encourage you to consider going out to the Brain Bowl. It's a fun thing. There's scholarship money available, as I think it told us that last time, Nikita or Russia told us. And you know, glory, fun, all of that good stuff. You get to go on some trips and do all sorts of cool, fun things that look great on transfer applications, all that good stuff. The other thing I want to remind you is that you need to be working on your honors projects. So a few people have been contacting me consistently and talking to me about their honors projects, and that's wonderful. I really appreciate that. But a few folks I've heard very little from, and we are approaching the midpoint of the semester. So you don't want to let this go to the end of the term and then try to rush it all out at the end. The honors project is worth a significant chunk of the grade. And it's something that you want to take the time to do well, not just for the grade reasons, but also because remember, you're going to be doing a presentation at the end of the semester. And that presentation is going to be not just in front of me, but in front of your classmates and in front of any other math faculty who choose to watch. We do invite the whole math department to come watch these presentations, and sometimes other people show up. One more thing I want to mention at the start here, of course, this is MAC2311. Section is OH1, so this is Calc 1 Honors. And today is the 18th of October, 2021. So some announcements. Please make sure you're working on the honors project. We talked about this at the beginning of the semester, but you do need to have a meeting with me to check in at least once through the term, where you show me your draft, your outline, whatever it is you have so far. And we can kind of talk through what you're doing and whether it's at the appropriate amount of detail, whether you need help with any of the specific mathematics. Of course, that's part of what I am here to do for you, is to help you with that math. So make sure you're working on the honors project, and remember to schedule at least one check-in meeting with me. Let's say before Thanksgiving break. And again, some of you have been coming and meeting with me like once a week to talk about your honors project. That's amazing. I really like that. Some of you I've heard very little to nothing from. So please, please, please make sure you're working on that. Your first step should be like choosing a question you're going to try to answer within your topic. You've already chosen your topics. Try to pick a specific question that you want to answer, or at least investigate a little bit. Your next step would be to do some research and write an outline. All right, so you do the research, start reading around as much as you can about your topic, thinking about your question as you read. And then you're going to write, just like you would for any other paper. If you haven't gotten in the habit of doing this, for the love of God, please do it. You're going to write an outline, right? Just a little skeletal outline. It doesn't have to have any details in it, but I'm going to start by introducing this and using these examples. I'm going to discuss this theorem and use these examples. I'm going to discuss this person's work and use these examples. Just very basic skeletal outline describing what your paper is about. That sort of structure is really helpful when you're going to write a research paper, trust me. The other thing I wanted to mention, I didn't notice this until recently, but the other thing I wanted to mention is that most did not turn in study guide 1. And I mentioned this, but maybe I didn't drive it home enough. To get the grades for the study guides, you need to submit the assignment here in Canvas. So remember, your study guides are not just a thing in WebAssign, right? You need to be writing out your solutions, and then you need to submit those solutions here in Canvas. The idea is, if you submit these before the test, I can go in and give you some feedback on your work, right? That's the whole point of the study guide. Otherwise, it would just be another homework. So the whole point of study guide 1 is that you solve those problems in WebAssign, you write out your solutions, and then you submit those solutions so I can like rate it and tell you, yeah, this looks great for the exam, or ooh, watch out for this on the test. You made a little mistake here. I don't want that to happen on the test. So please find that work. If you didn't submit this, I think I only had 1 or 2 people submit it. You know, one person submitted it. If you did not submit that written work for your study guide, you still need to do that. That's necessary. That's where the points come from. If you don't submit the work, I can't give you the points. It's not a huge thing, right? Each one is 25 points, but it is a meaningful thing, and altogether they're almost worth as much as a test. So you don't want to omit those. So if you didn't turn those in, if you didn't turn in study guide 1 in Canvas, please dig through your notebook, find the papers where you wrote those, where you solved those problems, and scan them and upload them. If those are long lost or something like that paper, you have no idea where it is, reach out to me. We can try to figure something out. I can open it up so you can go ahead and write out the solutions. I don't want to waste your time with stuff, but please look for those and submit them so I can give you the grades without too much headache. Remember to get the points for the study guides. You must scan and submit the written work for the problems.
I have a question. I already finished the study guide 1, but why in the Canvas it still shows study guide 1 didn't submit?
So that sounds like, give me 1 second here. So to get the points, you need to scan the written work and submit that in Canvas. So let me see what I have here for you. I can take a quick peek. So yeah. So Yiping and pretty much everybody else, with one exception, in order to get those points for the study guide, what you need to do is take your written work, right? The pages where you wrote down the solutions to those problems, scan them just like you did for your exam written work, or just like you would do if you're taking the exam online. Scan the work for your study guide and submit it to the assignment in Canvas here, right? So you go into your Canvas assignments, you go to study guide 1, and then you upload the written work for your study guide problems. So answering the questions in WebAssign is not where those points come from. I remember we talked about this very at the start of the semester, but maybe I didn't remind you guys enough as the test came around. So solving the problems in WebAssign is good, right? That's fine. But in order to get the points for the study guide, you have to scan and submit the written work. That's necessary.
I was emailed the study guide 1 draft to you. Did you read how much point will I earn? I just submit in the study guide again.
I do remember you emailing me. Yeah, I remember you emailed me yours and we talked about it through email. If you still have those files, you could just upload those files to Canvas. If you don't have those files, just send me another email saying, you know, these are lost, and I'll find them in my email and grade it that way. But generally, I would prefer if you guys submit them to Canvas, because that makes my life a lot easier.
How much point do I earn at that time?
I think you're in full credit. So the study guides, remember, the study guides are not graded for correctness. If there are mistakes on the study guide, that's okay. I'm just looking to see that you've tried each problem. As long as there is an effort for each problem, some work for each problem, I'm going to give you full credit on the study guide. The only way to lose points is to not try a problem. So the study guides are not meant to hurt you at all, right? They're only meant to help you. And the main point there is that by showing me your work before the test, like you did, Yuping, emailing me, I can tell you what needs to change or what we need to improve. So yeah, you don't have to worry about losing points. As long as you have some work for each problem, you're going to get full credit on the study guide. If you forgot to turn it in and you can find those papers, scan them and turn them in, that's awesome. If you cannot find them, then there's two options, right? Either I can open up the assignment in WebAssign for you so you can go back and write out those solutions again. Or you can talk to me. We can maybe see about doing something else, like an extra assignment in place of study guide 1, because I don't want you, grinding back through problems that you've already done. That doesn't sound very helpful, but I could give you something else to work on that you could show me the work for, and I could give you some credit for that as well. Okay, I think that's it as far as announcements are concerned. Last time we got to talk a little bit about the shape of a graph and how the derivative of a function affects the shape of its graph. Today, I want to talk more about graphing. We can talk a little bit more about how the derivative affects the shape of a graph. I want to solve at least one problem where we go through and find points of inflection, concavity, all of that stuff, because we didn't get to do that last time. I was able to define an inflection point for you, but we weren't able to do all of it. The other thing I want to do is introduce this concept, this tool called L'Hopital's rule. All right, so we are here. L'Hopital's rule is an interesting trick for finding certain limits. Turns out to be very useful when it comes to graphing functions, because a lot of the time when you're trying to graph a function, you need to know what's going on with horizontal asymptotes or stuff like that. L'Hopital's rule is a good trick for those. It also has a great story behind it. I don't know if anybody chose Pierre de L'Hopital for their honors project. I don't think anybody did this semester, but the guy after whom L'Hopital's rule is named is a bit of a thief in a funny way. He stole that theorem from somebody else. Or I shouldn't say thief, he's not. He actually paid for it, but he misrepresented his own skill. He claimed that the theorem was his own, when in fact it was paid for. He bought it from Johann Bernoulli. But before we do that, I want to wrap up section 4.3. So today, we're going to finish section 4.3, which is what we were doing last time. And we're going to cover section, so this was on how derivatives affect shape of a graph. And we're going to begin section 4.4 on something called L'Hopital's rule. The little symbol over the O there is called an accent circumflex. It's a French accent symbol. It basically means that in Latin, this would have had an S after it. So like instead of H-O-S-P-I-T-A-L, it's H-O circumflex P-I-T-A-L. So this is like hospital. Before we get into any L'Hopital rule stuff, I want to come back here though. So I'm going to begin by saying recall. I want to say this. A few main theorems from last time. Last time we said we have this theorem. It said if f primed of x is positive on the interval I, then f is increasing on I. Also, if f primed of x is negative on I, then F is decreasing on I. That was one of our theorems. We also had a theorem that said if F double primed is positive on an interval I, then F is concave up on that interval. Also, if F double primed is negative, crap there, on the interval I, then F is concave down on that interval I. And we talked about what concave up, increasing, concave up, decreasing, concave down, decreasing, concave down, increasing. We talked about those four graph shapes. And we talked about why the sign of the second derivative is what yields that shape, because the tangent lines would either be getting steeper, steeper, and steeper, which means you're looking at a concave up function, or the tangent lines will be getting, shallower, 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 a concave down function. If the tangent lines are increasing in their slope, then that's going to force your graph to have that concave up shape. And the way you get tangent lines increasing is if the derivative of f primed is positive, if f primed itself is increasing. So we looked a lot at the connection between the second derivative, the first derivative, and the original function, and how that influences the shape of the graph. Specifically, we had those four possible shapes. This was like increasing concave up. We had increasing concave down. We had decreasing concave up. And decreasing concave down. Right, and each of these four shapes is associated with a pair of signs. Increasing concave up means both f prime and f double prime are positive. Increasing concave down means f prime is positive and f double prime is negative, and so on, right? This would be f prime is negative, f double prime is positive. This would be both f prime and f double prime are negative. So these four possible shapes correspond to these two theorems together. We also had something called the first derivative test, which said if f goes from increasing to decreasing at a critical number c, then that critical number is the location of a max. And if f goes from decreasing to increasing at a critical number c, then that critical number c is the location of a min. We haven't looked at the second derivative test in detail, and we haven't looked at inflection points in detail. So I'd like to do both of those things starting now. First, an inflection point, recall, again. The function f of x has an inflection point or point of inflection at x equals c means the concavity changes. And remember, concavity is the sign of f double prime changes at x equals c. So you begin by trying to find some points of inflection, some inflection points, and eventually we'll build up to sketching some graphs. So let me grab an example here. Let's grab something Yeah, this is fine. No, is this always positive? No, let's do it. Okay, so x, yeah, let's take x to the 4 minus 4x cubed. So I'm going to say find the shape of the graph y equals, what was it? X to the 4 minus 4x cubed? Yeah. Regarding increasing, decreasing, and concavity. Right, so I want to find the intervals where this function is increasing, decreasing, and concave up, concave down. F of x here, this is y equals f of x, where f of x is x to the 4 minus 4x cubed. So f primed is 4x cubed minus 12x squared. Which I can factor. I can bring out 4x squared from this, and what's left is going to be x minus 3. Which means the critical numbers are 0 from this guy and 3 from this factor. So I can build a number line for f primed. I'll plot those two critical numbers. Here's 0, here's 3. And in each of these 3 regions that creates, my function will either be increasing or decreasing, because the derivative will be either always positive or always negative or whatever. We can test a point from each region. So if I test -1 from the far left region, that would mean I plug -1 into f primed. F primed of -1 would be 4 times -1 squared, which is 4, times -1 minus 3, which is -4. So this is -16, which is negative. The critical number x equals 2 comes from, or sorry, x equals 0 comes from this factor, which is a multiplicity 2 factor. So as we jump over 0, we're not going to change sign. This is one of those things from pre-calculus that I alluded to last time and posted something for you in the modules to take a look at. Sorry, let me see. Daniel, so if you haven't turned in the study guide 1 work, you can hand it in whenever. I'll take it. Please, just as soon as possible. The official rule in the syllabus is that the study guides are due on the day of the test. Again, the point of the study guide is not to penalize anybody. So if you forgot to submit that stuff, just get it to me as soon as you can. I won't take off points. Just please get it to me as quick as you can. All right. So this critical number 0 is coming from this multiplicity 2 factor. Since that's an even multiplicity factor, we will not change sign as we jump over that guy. So if we're negative to the left of 0, we're going to be negative to the right of 0. You could also test x equals 1 if you want. And if you plug in 1 here, then you'll get a negative number, right? This would be 4 times 1. This would be -2, so it'd be -8, which is negative still. The critical number x equals 3 comes from this factor, which is a multiplicity 1 factor. Since 1 is an odd number, right? That multiplicity is an odd number, we will change sign as we jump over that. So if you didn't get a chance to review the thing I posted on polynomials and multiplicities to the modules, I posted that last Friday, I think. Take a look at it. It saves you a lot of time. Or you could just test points in each of these regions. anything like that. The upshot is f is decreasing on the interval -infinity to 0 and the interval from 0 to 3. And f is increasing on the interval from 3 to infinity. That's the information we get out from this number line. We're decreasing here, we're decreasing here, we're increasing here, because f primed is negative, negative, positive. To find the concavity, we need the second derivative. And it's easier to take the second derivative from this guy than it is from this guy, right? Here I would use maybe a product rule or distribute this back through, and then I would get this and differentiate that with the power rule. So I'll differentiate from there. That's going to be 12x squared minus 24x, which can also be factored. This is 12x times x minus 2. So the numbers we put on the line for f double prime places where this thing could change sign are just 0 and 2. And again, we can test some points or use end behavior and multiplicity. If I test -1, then this would be -12 times -3. So f double primed of -1 is -12 times -3 is positive 36. In particular, f double prime is positive there. Now here, 0 is a root of multiplicity 1. This 12x is a multiplicity 1 factor, so we will change sign as we jump over 0 here. X minus 2 is also a multiplicity 1 factor, so we will change sign as we jump over here. So f is concave down on the interval 0 to 2, and f is concave up on -infinity to 0 and 2 to infinity. So here's all the information I need. Since f double prime changes sign at x equals 0, 0 is an inflection point for this function. Right? We go from concave up to concave down. My concavity changes here. So this is an inflection point. F also changes, or f double prime also changes sign at 2. We go from negative to positive, which means f goes from concave down to concave up. So there's another inflection point here. At x equals 3, f goes from decreasing to increasing, which means that this is a local min by the first derivative test. And 0, we already said, is an inflection point, although you wouldn't know it from this. Now, what we were asked to do is find the shape of the graph. So I'm going to draw one more number line where we describe just the shape. I'll put this on a fresh page so we don't clutter things too badly. Later in section 4.5, when we're sketching graphs like these, when we're sketching curves, I will ask you to make this final number line as well. So you're gonna do 3 altogether, one for f prime, one for f double prime, and then one for the shape of f. Shape of the curve y equals f of x. On this final number line, we're gonna put all of the numbers from the previous ones. So I'm gonna plot 0, 2, and 3 here.
I have a question before you draw the graph. Do you need to count about the 0 of the original graph first?
If we were going to draw the graph, yes. Yes, then we would want to find the roots of the original function as well. But here I'm just after the shape, so I'm not going to try to draw the whole graph. I'm just going to describe the shape, that concave up increasing for each of these regions. But yeah, you're correct. If we wanted to draw the graph of the function, in addition to these things, we would also want to know the x-intercepts and the local behavior near those x-intercepts, which would come from factoring the original. All right, let's see what we got. From negative infinity up to 0, I am decreasing and concave up. So I know here I'm decreasing and concave up. So what does that look like? That looks like this. From 0 to 2, I'm still decreasing, right? I'm decreasing from negative infinity to 0 and 0 to 3. So 2 is, right in here. So we're still decreasing, but now we're concave down. So decreasing concave down looks like this. From 2 to 3, we're still decreasing. We're decreasing all the way up to 3. But to the right of 2, we're now concave up. So that means we're now decreasing concave up, which looks like this. And then from 3 to infinity, we are increasing and we remain concave up. So that looks like this. And it's from this graph, or sorry, from this number line that it's easiest to draw the graph. In particular, you can think about joining these pieces together, right? And imagine what sort of things must be there. So if my curve goes like this and then like this, that's an inflection point. So right here, I have an inflection point. And we would want the ordered pair. The ordered pair here would be 0, 0, right? The x value is 0. And to find the y value, you plug into your function, which was x to the 4 minus 4x cubed. So that inflection point is of the ordered pair 0, 0. Moving left to right here, the next thing we see, we go from decreasing concave down to decreasing concave up. So we're still decreasing, but my concavity changed again. So I've got another inflection point. To find the y value of this inflection point, I would need to plug 2 into my function. So if I plug 2 in here, that's 2 to the 4 minus 4 times 2 cubed, which is 16 minus 4 times 8. And that's 16 minus 32 is negative 16. So this is a 2 comma negative 16. Now at x equals 3, my concavity stays concave up, but I go from decreasing to increasing. That means that's a local min. I'll just write min. And to find the point there, you would take x equals 3 and plug it into the original. So the x value is definitely 3. And if I plug 3 in here, I get 3 to the 4 minus 2 times 3 cubed. And that's 81 minus 4 times 27. Off the top of my head, my arithmetic skills are bad. 4 times 27 would be 108. Yeah, so 81 minus 108. Negative 27. So this is 3 comma negative 27. All right, so here we have done everything we could possibly ask you to do. You found the shape of the graph. From negative infinity to 0, we're decreasing concave up. From 0 to 2, we're decreasing concave down. From 2 to 3, we're decreasing concave up. And from 3 to infinity, we're increasing concave up. And each of those x values where something changes is an important point on the graph, either an inflection point or a min or max. I'm not going to go all the way and draw the graph here because there's a little bit more work that we would want to do, but I'll look at the graph in Desmos and we can verify that we did this correctly. Later, we will be drawing the graph, but I want to talk about L'Hopital's rule first. Here she is. All right, let's rescale our y-axis. What do we see here? Well, from negative infinity up to 0, we are decreasing concave up. Decreasing concave up. See how this part of the graph has that same sort of shape as this, right? We're going downhill, we're decreasing, but our tangent lines are increasing in their slope. They're very negative here, less negative, less negative, less negative, just like this guy. So decreasing concave up. Then at x equals 0, we switch to decreasing concave down. So we go from concave up to concave down, but we stay decreasing. Well, that's what we see here, right? I'm still decreasing over here, but now I'm concave down instead of concave up. My tangent lines are getting more negative with their slope. So f primed is decreasing, or f double primed is negative. From 2 to 3, we should be decreasing concave up. So right here, the concavity changes. We stay decreasing, but we go from concave down like this to concave up like this. And then from 3 to infinity, we are increasing and concave up, like we said. So this would be our final answer here, just this stuff. And it is true that we found 2 inflection points and a min. We can plot those points. Here's 0, 0, that's an inflection point. The other things we thought were inflection points, we had 2 comma negative 16. This is an inflection point. And then we had a min at 3 comma negative 27. It's a local min. It's also an absolute min. Not bad, right? Okay. Any questions about how we got this final number line for the shape of the function, shape of the graph? Okay. What I'd like to do is draw your attention to what's going on at x equals 3. I want you to imagine that I didn't already know that that was a min, but I did know that we were concave up everywhere there, and I did know that 3 was a critical number. If you are concave up and you have a horizontal tangent line, then that has to be a local min. The only way to have a horizontal tangent at some point and also be concave up everywhere in that region is if that horizontal tangent line is a local minimum. This is called the second derivative test. And there's a teensy bit of subtlety, so let me be very clear about this. If x equals c is a critical number, for f of x and f double prime of x is continuous, at x equals c, then if f double primed of c is negative, then you've got a critical number and you're concave down. The only way to be concave down at a critical number is if there's a max there. So this would mean f has a local, possibly also absolute, but definitely a local max at x equals c. If f double primed of c is positive, so if c is a critical number and you're concave up at c, then f has a local min at x equals c. That's just like this piece that we saw here at 3. If you go from decreasing to increasing, that would mean a local min. If you didn't know that, but you knew that you were concave up everywhere there and had a horizontal tangent line there, that would also be enough to deduce that you have a min. And if f double prime is equal to 0, then the test is inconclusive. Could be a min, could be a max, could be an inflection point, probably an inflection point, but we learned nothing. I'll say probably, or maybe an inflection point, but not necessarily. Not necessarily. It's possible that f double prime of c is equal to 0, but f double prime doesn't change sign. Maybe you've got a multiplicity 2 root of f double prime there. All right, so to use the second derivative test, first you do have to find your critical numbers. But the idea is you can skip over making the number line. You don't have to make a number line for f prime to find your mins and maxes. So let's try this, and let's try this on something fresh.
How do you know that f double prime is continuous at c?
Well, I don't know that. That's a hypothesis. So I'm saying if this is a critical number and f double prime is continuous. So in other words, in order to use this test, my second derivative needs to be continuous at x equals c. If my second derivative is not continuous at x equals c, then I can't use this test. That's all that's saying.
F double prime x is continuous at the c. It means if f double prime is a rational function and for the denominator is equal to 0 as c, so that is in continuous as c.
It's true, yeah. So if f double prime happens to be a rational function and the denominator, the bottom of f double prime, is equal to 0 when x is c, then we couldn't do this because then f double prime would not be continuous at c. So this is an important part of the theorem. You do need your second derivative to be continuous at least at that point. If it's not, if f double prime is not continuous at that point, then you're better off using the first derivative test. So the idea, let me fill in here a little note. The idea is that if f double prime is easy to compute, right, like a polynomial or something, if f double prime is easy to calculate, then finding the sign of f double prime at c is faster than making the number line for the first derivative test. Remember what the first derivative test says. The first derivative test says if you go from increasing to decreasing, that's a max. And if you go from decreasing to increasing, that's a min. So in order to use the first derivative test, you need to, I don't want to move the thing. In order to use the first derivative test, you need to make that number line for f primed. And that involves finding the critical numbers, yes, but also like testing some points or using the multiplicity trick. Sometimes it takes a little while to draw that number line. And if it's faster to go ahead and just find f double prime and plug C in, then sometimes this is a useful tool. It's going to be more useful to you in Calc 3. Let me tell you, really, the reason you're doing this right now is so that in Calc 3, where you are, let me turn on my camera here. In Calc 3, we're going to be studying functions of many variables. A function of 2 variables, for example, has a graph that is like a 3-dimensional thing, like a rippled sheet or some sort of surface, something like that. I can't talk about going from increasing to decreasing there because it depends on the direction, right? Imagine I've got just imagine a sheet with a little hill right here at the top, right? A 3-dimensional hill. I can't talk about going to increasing to decreasing unless you specify a path over that hill. If you say, I'm going to take this road over the hill, then yeah, I go from increasing to decreasing. But in a 3-dimensional space, there is no like go from increasing to decreasing. Your input space is 2D. But there is a higher dimensional version of the second derivative test. And I can say, okay, if my graph has this sort of concave down shape, and I've got a critical number there, then that has to be a local max. Or if my graph has this sort of concave up bowl shape, then even though I can't talk about going from decreasing to increasing, I can say, oh, well, if there's a critical number there, that has to be a min. So this is like the 1-dimensional version of a test you're going to use in Calc 3 when you have 3 or higher dimensional graphs.
I think that the second derivative test is plot the critical points into the f double prime x to test is greater than 0 or less than 0. But the critical point also is solve the critical point is from the f prime x for those 0 of the f prime x and also the undefined of the f prime x, right?
That's correct. Yeah, it's possible that you have a root of both the original derivative and the second derivative. And in that case, we don't learn much from the second derivative test. But okay, let's start with something simple like number 19 here. Let's use, they say use the first and second derivative test. We've already practiced a good amount with the first derivative test. So for number 19 here, I'm going to say use the second derivative test to find mins and maxes. Let me write this down and then I'll switch back to the document camera. Okay, and we said x cubed minus 3x squared minus 9x plus 4. So let's use our second derivative test to find mins and maxes for this thing. Well, I need to first find critical numbers. So I'm going to calculate my first derivative, which is 3x squared minus 6x minus 9. I can factor out a 3, and I get left x squared minus 2x minus 3. And then I can factor this quadratic, right? I'm looking for two numbers whose product is -3 and whose sum is -2. That's x minus 3 times x plus 1. F prime is never undefined. So the critical numbers are just these two numbers, x equals 3 and x equals -1, the two places where f prime is equal to 0. I could now make a number line for f primed using this factored form and deduce my mins and maxes from that. Or, because I want to use the second derivative test, compute f double primed, which is going to be 6x minus 6. This is continuous everywhere. So I can use my second derivative test, right? This is a linear function, definitely continuous. F double primed of 3 is 6 times 3 minus 6, which is 18 minus 6, which is 12, which is greater than 0. Which means that f is concave up at x equals 3. So I have a horizontal tangent line and I'm concave up. This means that the critical number x equals 3 is the location of a local min, right? If you are concave up and you have a horizontal tangent line, got to be a min. That's what the second derivative test is telling us here. On the other hand, f double primed of -1, that's 6 times -1 minus 6 is -12, which is less than 0. So that means I'm concave down, right? And if I have a horizontal tangent line and I'm concave down, that means there is a local max at the critical number x equals -1. So that's it. I've got a max at -1 and a min at 3. Done. Not bad, right? Now, would it have been hard to make the number line for this? Nah. Now we could have used the first derivative test here also, but the second derivative test wasn't bad. I wrote more than I needed to write. I'm just trying to be very, very clear to you when I write these things down. But you say, oh, okay, f primed of 3 is 0, f double primed of 3 is positive, so that's a min. F primed of -1 is 0, f double primed of -1 is negative, so that's a max.
I have a question. If the f double prime x plot the critical number into the f double prime x is equal to 0, how do I continue for that job?
Yeah, so if that's the case, then we don't learn anything from the second derivative test. So if f double primed of your critical number is 0, then the second derivative test is not the way to go. You'll either use the first derivative test or something else. So if we were to discover, for example, that when we plug 3 in here, we get 0, then I would say, ooh, I didn't learn anything from that. I better go back and use the first derivative test instead. Okay. Let's try another one. How about 21? How about root x minus the fourth root of x? This time I'll say we can use either method. So find mins and maxes for f of x equals square root of x minus the fourth root of x, using either first or second derivative test. So it's up to us. Here's how you choose. Go ahead and take your first derivative. You're going to need that no matter what, right, to find your critical numbers. After you find your critical numbers, ask yourself, would I like to differentiate this again to use the second derivative test, or would I rather make a number line for the first derivative? Whichever one feels like it's going to be easier is what we should do. Here, f of x is x to the 1/2 minus x to the 1/4. So f primed, my first derivative, is 1/2 x to the negative 1/2 minus 1/4 x to the negative 3/4. Just the power rule. Does anybody know the trick for cleaning up and factoring things like this? There is a nice algebra trick here. This is not a polynomial. No? Okay. What you do is you force factor the largest negative exponent term. That's the algebra trick. So I've got an x to the negative 1/2 and an x to the negative 3/4. The one that has the largest negative exponent is x to the negative 3/4. So I'm going to force factor this out. Before I even do that, I'm going to force factor out a 1/4, just to give you an idea of what I mean by force factoring. So if I force out a positive 1/4, and factor out this number. When you factor out the 1/4, this piece is just going to become x to the negative 3/4. The power of x here will not change. That will still be x to the negative 1/2. The minus between them stays the same, but what happens to this? What is the new coefficient of x to the negative 1/2?
2.
2, very good, 2. So we ask, what must go here in order that when we distribute the 1/4, I get the 1/2 here. Another way to say it is I'm dividing both of these terms by 1/4. When I divide this term by 1/4, the 1/4 just cancels, it goes away. 1/2 divided by 1/4 is 2. So this is what force factoring is. It's where you factor something out, even if it's not a common factor. Now to use my trick, I'm going to force factor out x to the negative 3/4. So I'll have 1/4 x to the negative 3/4. Over here, I'll have now just -1. Right? When I factor out x to the negative 3/4, this piece becomes just a 1. The 2 here will stay a 2. I'm not doing anything with the constants. What is x to the negative 1/2 going to become if I divide that by x to the positive 3/4?
Well, exponents, you end up with negative 1/2 minus, no, it's going to be plus 3/4.
Very good.
And then you just have to you solve for the fractions. Yeah.
So the power here, I'll write it exactly as you said it. In fact, I'll write it like this: negative 1/2 minus negative 3/4. So that's really what's going on, right? I'm dividing out by x to the negative 3/4, so I'm subtracting that power. So this is 1/4 x to the negative 3/4 times 2x raised to the negative 1/2 plus 3/4. Okay, what is that? Negative 1/2 is negative 2/4. Negative 2/4 plus 3/4 is 3/4.
1/2.
Let's be careful. So negative 1/2 plus 3/4 is negative 2/4 plus 3/4.
1/4.
Which is, yeah, positive 1/4. So this will be x to the positive 1/4 here, minus 1. All right. This is our first derivative in its most useful form, perhaps. I can rewrite this one more time. This is 2 times the 4th root of x minus 1 divided by 4 times x to the 3/4. All right, this is my derivative written as nicely as I could. The other way to get here, BT dubs, is to rewrite each of these as fractions, 1 over root x, 1 over x to the 3/4, and then have a common denominator and combine all the like terms. It's a little nastier if you do it that way than doing it this way. And this algebra trick is especially useful when you have pieces that come from the product rule. But in any case, I'm looking for critical numbers now. So the critical numbers are places where f primed of x is either 0 or undefined. Where is f prime undefined?
If x equals 0.
Good. Now remember, critical numbers also have to be in the domain of the original function. Is 0 in the domain of this function?
Okay.
Yes, it is. Yes, it is. I can plug 0 in here, no problem. The square root of 0 is 0. The 4th root of 0 is 0. So this is our first critical number. F primed is equal to 0 if and only if the top of this fraction is equal to 0. So it's 2 times the 4th root of x minus 1 equals 0. So I can add the 1 to both sides. I get 1 equals 2 times the 4th root of x. I can divide both sides by 2. So I get 1/2 is equal to the 4th root of x. And then I can raise both sides to the 4th power. So I get 1/16 is equal to x. And 1/16 is also definitely in the domain here. The domain of the original function is 0 to infinity, including 0. So it was a bit of work, but here are my critical numbers. All right, happy fun time. Would we rather make a number line for this or differentiate it again and plug in?
Number line is going to be way less messy.
It's kind of, yeah, it's honestly, I find myself conflicted from time to time. At this point right here, I wouldn't mind differentiating again, but plugging numbers into that thing could be a little nasty at the end. On the other hand, making a number line for this could itself be a little bit nasty because I'm going to have to test points. So we can try it either way. Let's go ahead and try using the first derivative test. See how bad this is. My critical numbers are 0 and 1/16. You do want to make sure you plot these in order, right? If something is smaller than one of the critical numbers is smaller, then it needs to go to the left. The domain of both the original function and the derivative don't include any negative numbers. So this is outside the domain. Between 0 and 1/16, this is a little tricky on its own, right? What on earth am I even going to test in here? Can't test 1. 1 is way over here. Can't test 0. I need to test something between 0 and 1/16. We'd go with like
1 over 81.
Yeah, I would like to pick something whose 4th root is nice because I have to take the 4th root in 2 different places here. So let's pick
1 over 81 will get you a 3. 1 over 3.
Yeah, good. Let's test x equals 1 over 81, right? Because 81 is a perfect 4th power. It's 3 to the 4. If I plug that in here, let me do the calculation down here. F prime of 1 over 81 is 1/4 times 1/81 to the -3/4 times 2 times the 4th root of 1/81 minus 1. A little bit gnarly, a little bit gnarly. This is 1/4. 1/81 to the -3/4 is 81 to the +3/4. I can do that. And then 2 is 2. The 4th root of 1/81 is 1/3. So this is 1/4 times the 4th root of 81 is 3. So this is 3 cubed is 27 times 2/3 minus 1, which is -1/3. So this number, whatever it is, it's definitely negative. So we start off decreasing. F prime is negative at the start. And then we can test anything to the right of 1/16. We could test x equals 1. F primed of 1 is 1/4 times 1 to the -3/4 times 2 times 1 to the 1/4 minus 1, which is 1/4 times 2 minus 1 is 1. So this is positive, which means the graph feature at 1/16 has to be, well, decreasing, and then I'm increasing. This has to be a min. What about over here? There is nothing to the left of 0. But everywhere from 0 to 1/16, I'm decreasing. So this left endpoint here has to be the highest point in that interval. This is a max. Right? If I start at x equals 0 and I decrease, then turn around, increase, this left endpoint, and I know this is going to bug some of you, is a local max. And this is a local min. Let's take a look at the graph. We need to reset these axes. Let's go from -1 for now. Yeah. And then from like 0 to 2. All right. So here we see it, right? We've got a max at 0. Whether we like it or not, this is a local max. It's the tallest point on the graph nearby. And we've got a min here at 1/16. This is a local max. And at this point down here, I have a local min.
If you don't draw this graph in the decimal, how do you know that is the local max at 0?
So the trick here, we do that beforehand, right? The trick here is that I know that my graph is, if we draw the, I know that my graph is decreasing. So let's see, I'll put it over here. We know that f is decreasing on 0 to 1/16 and increasing on 1/16 to infinity. The max at 0, the domain of f, is the left closed interval 0 to infinity. like this. So kind of I know I'm starting here and I'm decreasing until I get here, and then I turn around over here. And in particular, I know that there is nothing over here. So if f of 0 is defined and there's nothing to the left, then this couldn't have been decreasing over here. It couldn't have been increasing over here. There's nothing going on over here, which means this starts out at a local max. It means that if I kind of zoom in on this part of the graph, right, if I'm just looking at like this little part of the graph here, that point is going to be the tallest point anywhere in that region. So again, this does come down to that little issue where the book doesn't like to consider endpoints local maxes. But if you're looking at this graph, yeah, that's the tallest point on the graph anywhere nearby. So what if there isn't anything to the left? If you look at any other y value on this graph near x equals 0, it's going to be smaller than this y value. So that is a local max. And then the local min here is nothing weird, right? This is normal stuff. You go from decreasing to increasing. All right. Is this easier or harder than the second derivative test would have been? How much time do I have? Let's go ahead and crunch out the second derivative.
Can I say the domain is because the f of x domain is from 0 to the infinite. So for the local max is 0, 0, 0, 0, and the local it doesn't have the local it doesn't have the local max in the 1/6 to infinite.
That's true. There is no local max over here. Certainly that is true. But it's not every function has a local max. So it's possible, like we can't say that there must be a max at 0 because there isn't one somewhere else. Like the process of elimination wouldn't work there because there are many functions that don't have a local max at all.
And also this kind of question in the exams, you will point the local max include of endpoint.
Yes, so if this was a question on the test, I said find all the mins and maxes for this function, I would say include endpoints as local extrema. I would say that endpoints still count. You have to worry about endpoints. And I would say that in the question.
Thank you.
Of course. All right, let's try the second derivative test instead. So that was a lot of work. Maybe the second derivative test is faster. Well, there's going to be some issues. F double prime is not continuous at 0. Let's go ahead and compute it. This would be 1/2 times -1/2, which is -1/4, times x to the -1/2 minus 1 is -3/2. And then we would have minus -1/4 times -3/4 is positive 3/16 times x to the -3/4 minus 1 is -7/4. So f double primed of 0 does not exist. Oops. Can't use that. Right, you can't raise 0 to a negative power. But this would be very quick, I think, for f double primed at 1/16. Because this is -1/4 times 1/16 to the -3/2 plus 3/16 times 1/16 to the -7/4. And these are not terribly hard things to compute, right? The 3/2 power of 16, this is -1/4 times positive 16 to the positive 3/2 plus 3/16 times 16 to the positive 7/4, which is -1/4 times 16 raised to the 3/2 power is the square root of 16 cubed, which is 4 cubed, which is 64, plus 3/16 times 16 to the positive 7/4 now. We flip the fraction, positive 7/4. The 4th root of 16 is 2. So this is 2 to the 7, which is 128, I think. So 2 to the 5 is 32. 2 to the 6 is 64. Yeah, this is 128. So 64/4, that's -16. 128 divided by 16, what is that? Is that 16? 128 divided by 16. It's 2 to the 7 divided by 2 to the 4 is 2 to the 3 is 8. Okay, so this is plus 3 times 8, which is -16 plus 24, which is definitely positive. That's positive 8. So f double prime there is greater than 0. So x equals 1/16 is a local min by the second derivative test. So the second derivative test is pretty quick for finding the local min at 1/16. Faster probably than the number line work, but it
But I
won't
have
help
a
us get
question.
the point on 0.
F prime of zeros it doesn't works in the second derivative test. So do I need to do any process for the f prime of 0?
Well, yeah, so kind of the take-home lesson here is if you want to detect both of these, if you want to catch the min at 1/16 and the max at 0, then you really would need the first derivative test. But if you're not worrying about endpoints, right, if we're excluding endpoints from our local extrema, then the only thing we have to worry about is the 1/16. And that we can get very quickly with our second derivative test. So it depends on what you're trying to do. If the problem, like many of these homework problems, say don't consider endpoints as local extrema, then you're only looking for what's happening at 1/16. And that would mean the second derivative test is probably faster, right? This was not too bad. If you're looking for everything, including endpoints, then you would need to use the first derivative test because the second derivative test doesn't work here.
The homework never actually specifies, like in the problem description or what they're asking, to not use endpoints. It'll just mark stuff wrong if we do.
Really?
I'm assuming that on the test you'll be, yeah, it never actually says like don't use endpoints. It just will mark it wrong if we do. I figured out the thing with endpoints because as soon as I took out my endpoints, my answers were correct.
That's frustrating. It used to say exclude endpoints. It used to say explicitly, and they must have removed that in the latest edition. That's a bummer. Well,
But is it generally
And,
safe to assume they don't like it?
how do I get the endpoint if how do I get the endpoint if endpoint is maximum or minimum? How do I know the endpoint is maximum or minimum?
So that again comes from our first derivative test, right? Once we have this will tell us everything.
So actually in the exam, I just use the first derivative test will be better.
Depending on the question, yes. So if the question says to include endpoints as local mins and maxes, then the first derivative test for this problem at least would be the better path. Let me say this. So if the textbook and the homework are implicitly saying that you cannot use endpoints as local extrema, it kills me to do this. I'll adopt that same convention. It's wrong, but if that's the case, if the textbook is implicitly saying that rather than explicitly telling you from problem to problem, I'll adopt that same convention. So on the test problems, I'll still make clear, I'll still say in the problem, don't consider endpoints as local mins and maxes. or at least something like that, because I don't want this to be any more confusing than it needs to be. So let's say it this way. The second derivative test is most useful when you're looking for a local extrema that do not come from endpoints, and your second derivative is easier to plug into than your first derivative is to make a number line for. That's sort of the big take-home message here. The most fun stuff I can do with the second derivative test, and I'll end after this, is stuff like this, right? I tell you f double prime is continuous, and I give you some values of the first and second derivative. What can you tell me then? These are the sort of things that we like to ask. So given this kind of information, what can you tell me about the function f at 2 or the function f at 6? Those are the sort of things that I would want you guys to be able to remember from the second derivative test. All right.
Cool, thank you.
All righty then. So I'm going to go ahead and close the meeting for the day. If you guys want to talk, I do have an office hour this afternoon from 1 to 2 p.m. where you can, as always, send me Canvas messages, talk to me on Discord. I think the Discord invite links have expired. Does anybody need a fresh invite link, or do we all have that server saved? It sounds like we all have it. Maybe I'll update that link just one more time. But that's it for today, guys. I'll see everybody on Wednesday. On Wednesday, we're going to talk about L'Hopital's rule. So we didn't quite get there today. That's fine. Wednesday, we will talk about L'Hopital's rule, and we'll begin this business of curve sketching, where you use all of this information, concave up, concave down, increasing, decreasing, mins, maxes, blah, 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 to graph the original function. And those are very, very fun problems. Those are things like this. We will get to that next time. But for today, just worry about using the first and second derivative tests to compute mins and maxes. It's going to be a fresh homework. It'll have a mix of both. If you want to get started, definitely start worrying about finding mins and maxes. We'll move on from there next time. All right.
Sorry, you just said post a link. What kind of link did you say?
Oh, Discord. So remember, we have a chat server for this class. And I think the invite link that I posted to Canvas's announcements has expired. So this is our Discord, right? And
yes, I used Discord, ask some questions, but nobody answered.
Oh, that's a shame. I will try to get in here and moderate this a little bit more actively. But yeah, I'm sorry if we've been a little bit behind on that. But I'll go ahead and update that link anyway, so we can come in here. It is a nice place for you guys to talk to each other. That's the main point here. So please do try to get in there and respond to your classmates. If you can't, that's okay. But it's a nice thing because you guys can't really chat outside of class the way we normally do. But that's it. I'm gonna go ahead and end the meeting here for today. I will update the Discord link. If you guys feel like using it, please do. If you don't, that's understandable also. But try, because the more you can build a community, the more you talk with each other, I think the easier you'll find all this stuff.
Thank you so much.
Of course, of course. All right, gang, I gotta get running, but I'll see you guys on Wednesday. Take care.